Welcome to today's lecture on data preparation, a crucial step in any data science project. I am Dr. Andrei Holtz, and we will explore why data preparation is the cornerstone of machine learning. Without it, even the best algorithms will fail. Imagine training a model to predict heart disease. With missing or incorrect patients' data, the outcomes could be dangerously wrong. Today we will learn how to ensure data quality to build accurate and insightful models. During previous lecture on exploratory data analysis, we highlighted key challenges. It was dealing with missing data, managing inconsistent data, identifying outliers, handling high dimensionality, and addressing data imbalance. During this lecture, we'll cover missing data and outliers, and we'll leave high dimensionality and data imbalance for another lecture. So let's focus on those challenges. Today's agenda will understand the role of data preparation in machine learning pipelines. Then we'll go to data cleaning and talk about missing values, duplicates, and outliers. Then we'll move to data transformation and encoding, following the data preparation challenges, and then we'll have a summary and wrap up. Let us move on. And to understand data preparation in context, let's take a look at the CRISP-BM framework. You probably remember this CRISP-BM diagram from the previous lecture. We covered the data understanding step during the exploratory data analysis, and now that's a data preparation step. So let's move on and see in details what it includes. Although data preparation is repetitive, but it is essential. It contains of selecting the data, cleaning the data, constructing data, integrating and merging the data into data set, then formatting data, and in the end you have a data set. Ideally, after the dataset preparation, you should have the dataset description or the dataset card describing each feature, describing how the feature was collected, created, and it's a kind of internal documentation that helps you understand what was going on and how you ended up creating this data set. So let us move further and talk a little bit about the data preparations. Data preparation can feel repetitive and boring, but it is essential. Think of it as building a house. No matter how well designed the walls or roof, without a strong foundation, the house won't stand. Data preparation is this foundation. It ensures your data is reliable and ready for analysis. It takes up significant amount of time, but quality data in means quality insights out. So as I mentioned, not only garbage in, garbage out. Let us hope that we have quality in and insights out. Importance of the data preparation is crucial. Consider healthcare data where missing values are not addressed, and this could lead to serious biases in model predictions, or a financial data set with extreme outliers in transaction amounts. These could skew the model. Thoroughly cleaning the data, handling outliers, and filling in gaps ensures that our model are reliable. Today, I want you to see data preparation as a way of reducing uncertainty in the data and in the results. As for the data preparation steps, we can break down them into this collection that you see on the screen. It's data collection, just gathering all necessary data from relevant sources. We won't cover this during the lecture. Data cleaning and data transformation and encoding will be covered during this lecture. As for the feature selection, feature generation, dimensionality reduction, that's a topic for a separate lecture. We will cover this. And the same goes for data splitting, cross-validation, data leakage prevention, and building data pipelines. We will cover them during the upcoming lectures after we take a look at some machine learning models in order to use the models in the pipelines. Let us move to data cleaning. Data cleaning ensures our dataset is complete, consistent, and accurate. Imagine a heavy dataset where age, income, and gender are the features. If some rows are missing income or have incorrect data types for gender, the model's learning process will be compromised. And data cleaning involves correcting those issues, filling in missing values, removing duplicates, and standardizing formats. So again, clean data leads to more accurate models and better decision making. The first step is missing values. Missing data is common and occurs for various reasons. Entry errors, technical failures, participants refusing to answer. There are numerous ways you could have missing data. Missing data can be categorized into the following three buckets. So it's missing completely at random, MCAR, missing at random, and missing not at random. Understanding why data is missing helps us choose the appropriate handling method. For instance, MCAR, completely at random, can be deleted without bias, but MAR and MNAR require more careful imputation or deletion. I can give you some examples. Missing completely at random. The probability of a value being missing is the same for all observations. For instance, imagine we're having a survey, and the survey is about, let's say, the income level. Survey responses are missing because some participants randomly choose not to answer. They just don't like to answer surveys in general. Nothing to do with the data or with the question. Missing at random or missing conditionally at random. The probability of missingness is related to some of the observed data, but not to the missing data itself. For instance, older individuals are less likely to report their income in a survey, and the missingness of the income value in this particular case depends on the observed characteristics, age, but not on the income value itself. And as for missing not at random, people with higher incomes are less likely to report their income, and the probability of missingness for this particular survey will be related to the value of income itself after a certain level of income, of course. That's the idea behind it. How we handle this? It's either deletion or imputation. And what about methods for handling missing values? As for the deletion, you can either remove the whole column. Imagine like you have only 10% of the data and everything else is missing data, you can drop it. The second option is you can drop rows from the data set that contain missing data. Again, not the best option because you are losing the data. A list-wise option is also a bit tricky. In this case, you remove missing data only if it is included in some calculations. If not, you're keeping it. Again, not the best option because your metrics, your calculations won't be consistent, so they will be biased. What about the imputation? Here you should take into account the type of the data you're dealing with, whether it's time series data or general data. So for the time series data, it also depends whether there is seasonality trend or there is no seasonality in trend. I won't stop here. Like in details, we'll discuss this time series imputation during the time series lecture. As for the general data, so it depends whether it's categorical or numerical, but in general, you can use mean, median, or mode. It's a straightforward approach. You can use some models, like you can use predictive modeling, just try to predict the value of this missing spot. Or you could use some information about the neighbors. Let's say you select the similar objects and just mark this missing spot as the most common around the neighbors. Again, we will cover some of them during the practical session. And as I mentioned, there are several approaches and techniques like this meme. It's usually, data is not missing, it's just relatively unknown. We will cover the methods for imputing during either the practical session or during the next lectures on the specific topics. Let us have some coding and we'll take a look at the missing values how to deal with them, which techniques should we use, and what are the tools to do this. Hello and welcome to the demo of the missing values analytics. We'll start with the routine. Let us mount the Google Drive, load some libs, and load the dataset. We'll be using the housing dataset. For this dataset, we have description. It will be useful later on. And let us start with a simple missing values analytics. Let us count everything that is null. Here we can see per column countings, and some of the values are pretty high, I would say, especially like pool. QC means pool quality. Let us visualize the missing values. We can do so by applying the color palette that is like gray. For our convenience, you can use whatever color palette you like using Seaborn heat map. And here you go. And as you can see, LA, the pool, and some others are almost empty. It might indicate that those values, those missing values, are actually not missing. They're just none. And means that what is meaningful is the existing of the value, not the like emptiness. Let us sort the values and see. Yeah, 99% of the pool quality is missing. I would say it means that 99% of the houses have no pool, meaning none at pool QC should be like category. And that brings us to the missing values type. Like missing completely at random, MCAR, missing at random, MAR, and missing not at random. Let us calculate the example of different types of missing values, and we'll imitate them by using masks here, applying to the ground living area. We'll also use t-test to compare the means of the original and simulated datasets to check if the differences are statistically significant. We set the p-value at 5% level. So in order to check MCAR completely at random, I'm just masking completely at random the 5% of the dataset. We'll calculate the statistics, the changes, and so on. As you can see, like the change here is like 5% in count. However, it almost did not affect the mean, 0.3% of change. It affected the mean, the minimum value, but in general, and the t-test confirms that the change is not statistically significant if we take a look at the mean value. Let's move on to the MAR. This MAR means that the missingness is related to other observed variables, but not to the value itself. We will use the garage type detached as a reference to simulate this. If the garage type detached, it will be none. We'll just calculate everything. So this, again, just a reminder, this is our simulation. We calculate all the statistics. Let's just see what we have. Data with MAR simulated for this one is 700. We can see that the change in count will be 26, almost 27%, leading to 5% error in mean. The change is statistically significant according to t-test. What about NAR? So it's not at random. Since the missingness is related to the value itself, let us just cap it. And if the ground living area is above some threshold, we'll just place nan here and calculate all the statistics once again. We can see that we have almost 10% change in mean and 34% change in standard deviation. Let us take a look. What was the change for the standard deviation in MAR? It was 5% in mean and less than 1% in standard deviation. And here we have 34%. That's a huge change. And of course, this change is statistically significant and it is detected by the t-test. Going back to the pool quality, let's take a look. I calculated here the mean sale price for different pool qualities, including none. And what we can see here is when there is a pool and it is of a good quality, the price is higher than for the NaN, meaning that if there is no pool, the price might be higher. And I think that's meaningful. The same actually goes for other features that we mentioned, and you can take a look at the percentage here. Let us just introduce another category and use none as a category here, because obviously that's a category. Let us check the listwise and pairwise deletion. So listwise, like the simplest one. Just let us drop the rows where there is none. That brings us to the loss of 24% of the data if we remove rows where there is a none. And as for the pairwise, let us imitate the nonce, the level of 5% randomly. Let's take a look. So what if we just get rid of some values? I mean, we use pairwise deletion, meaning that we remove only the data if we need to calculate something that cannot use nonce. Let's take a look. For this, we have like pairwise removal of 5%, since we imitated those 5%. As for the correlation matrix, we can see a change here, but it's not dramatical actually, so it's like the third digit, since we're removing 5% of the data. Imagine now we successfully identified the outliers. Now we need to impute them. Let's start with the simple imputing methods. We'll use the copies of the dataset. We'll start with the mean imputation for the numerical column. You can use simple imputer from the Scikit-learn impute. Of course, you can impute the data by yourself. However, I highly recommend just use Scikit-learn's impute. Take a look at the documentation. So at the parameters here, you can set up the strategy type, field value, copy, indicators, and so on. As for the strategies like mean, median, most frequent, constant, filling value for the constant, and all the attributes, keep empty features, add indicator, just use it. Of course, if you want, you can create your own or use some other tool, but Scikit-learn is a great leap, so please use it. We'll use it heavily later on. Let's move to the most frequent, apply to garage type, and constant. Now, since we applied all those simple imputing methods, let us calculate statistics. As we can see here, the mean did not change since we imputed the mean, but the mean changed when we used constant. And again, just a note, for some distributions it's better to use median, not mean. It highly depends on the type of the distribution. Which one to use? Well, it's a tricky question. It highly depends not only on the data set and the distribution of the data, but also on the machine learning model that you are using. I think we'll cover those nuances during the feature engineering part. Today, we're just taking a look at the imputation approaches. Let us calculate the statistical significance. As expected, mean imputation did not significantly change the distribution. However, constant imputation did change the distribution. Let's take a look at the categorical. Well, nothing changed, but that's a toy example. Sometimes it might change if you have a huge amount of missing values. Let's take a look at the advanced imputation techniques. Those include machine learning modeling like KNN imputer, iterative imputer, some linear regressions, and so on. We won't stop on the exact implementation and details of the implementation. We'll just use those tools to impute missing values data. Let's take a look. The missing values for lot frontage is 400, almost 500, and garage type is 157. Let's start with a linear regression imputation for numerical values. What it does, we just train regression on the existing data and fill the missing data. That's a toy example, so in order to make it robust and clear, you'll need to have more sophisticated pipeline, but this is a toy example. I'm just showing you how to use it. It is applied, so yeah, as I mentioned, train and test, just sanity checks here, like have a predicted value, and we impute the null values with the predicted values. What about nearest neighbors imputation? K-nearest neighbors is a machine learning method to find the neighboring objects of your object, meaning that in some metric, in some plane, they're close to each other by some distance. You can take a look at the detailed explanation of the nearest neighbor imputation, but the idea is, let us find the objects that are close to this one and use their values to fill missing values for our object. Yeah, and we apply this and we'll later take a look. So, and as for iterative imputer, it is similar to the linear regression. It uses more sophisticated regressor, but again, it fits on the existing data and predicts the missing data. That's the idea. Again, it is an existing iterative imputer from Scikit-learn, so as the KNN imputer. You don't need to write your own. What about the categorical values? Well, there are sophisticated approaches to use, but let us be simple and we'll just use the existing simple imputer with the most frequent. Let's take a look at the statistics. As we can see, like the mean changed a little bit depending on the different type of imputation, but that's not a great change. Yeah, same for the standard deviation. Let us calculate the statistical significance of change in means. As we can see, the statistical tests show that the difference is not huge. It's almost the same distribution. What about the categorical imputations? We'll calculate the chi-square significance here based on the imputations, the most frequent and the simple imputer, like they're the same actually. Well, the change was not dramatical. Let us visualize the imputation effects. We'll plot the data and take a look how it changed. We have here the density plot for plot frontage. Here you can see the original and the imputed data, and each of the approaches changed a little bit here, like changed the data a little bit. We can see here the result of the imputation. For each method, the density is a little bit different, however, it still remains in the same distribution. That's for the categorical data. We can see the attached as the most frequent had more values here. This is just an interpretation, p-values, and so on. That is it for the missing values. Welcome back, and let us continue. Duplicate data entries can distort our model's learning. For instance, if customer data is repeated multiple times, the model might overestimate the importance of certain customer behavior. Removing duplicates ensures that every data point is unique, reducing the bias in learning process. That's pretty straightforward approach. You just look through the data or just analyze the data and try to find exact matches of the data and just get rid of it. We don't need like the exact matches of the data. However, we need to be sure that the exact matches are really duplicates and not some meaningful data. That might also happen, so just keep in mind the situation and the domain. So maybe in your specific case, that's not a duplicate, it's just another object. Okay, and let's talk a little bit about outliers. So outliers are extreme data points that derive from the rest. For example, if employees' salaries fall between 40,000 and 70,000, but there are a few above 1 million, those are outliers. Outliers can result from errors, or they can also represent unique, valuable cases. Depending on the context, we might choose to remove them, keep them, or transform them to reduce their impact. And what about traditional outlier detection methods? Well, there are plenty of them, and some of them you can see In this slide, we can use like scatter plot and visually inspect the data, or box plot for visual inspection. And also we can have simple statistics like IQR, interquartile range, or Z-score, or Cook's distance. Z-score measures how far a point is from the mean. Typically, outliers are beyond 3 standard deviation. That comes from the normal distribution. IQR. Points outside of 1.5 times the interquartile range are flagged as outliers. And Cook's distance, it identifies influential points in regression models that may disproportionately affect the model. It is calculated by the formula, and we'll take a look at this distance on the practical session. So those are illustrations. You can clearly see here the different approaches, the IQR distance calculation, the probability of some point being in a specific place of in the distribution on the box plot here. So, and what about the advanced outliers detection techniques? Well, you can use k-means, like basically you can use machine learning and modeling to identify outliers. So k-means, dbScan, and all those approaches are ML-based models. We'll definitely take a look at them, but I want you to know that there are different ways to detect an outlier, and not only by classical statistics, but also with the machine learning. For instance, k-means, just outliers are points far from the cluster centroids. dbScan, outliers are in low density regions where no clusters can form. And isolation forest is a way to use the decision tree. We'll discuss like decision trees in lectures a bit later, not during this one, but those are tree based. And yeah, so there are like advanced outliers techniques, and we can take a look at some of them. Yeah, so using dbScan, as I mentioned, here like circled are outliers. There is a low density around them, and the points here, like in the bottom, the red ones, are like with the most density. Decision tree can be used to find outliers. Outliers are few and far from the rest of the observations, and we can use this logic to try to isolate them. We can use deep learning based techniques. I won't stop here for long because this requires a fair amount of understanding of the deep learning, but we'll get back to them during the deep learning sessions. Time series and multivariate outlier detection is also an option. We'll discuss those options during the courses, the lectures of time series. So for you just to know that there are options to do so. Let us move on. Imagine we have successfully identified outliers. So what should we do next? There are several options for this. We can remove, that's the easiest way. We can impute them with more appropriate values. Or we can transform them. We can apply some transformations to the feature and minimize the effect of the outliers. As for the removal versus keeping, so it is safe to remove the outliers if their nature is like errors or they're just irrelevant. But it is important to keep if the outliers are informative, for instance, such as fraud detection or like salary outliers for some cases. This is a thing to keep in mind when you deal with the outliers. So just do not only remove or keep or impute them. You should understand what is behind those outliers. For instance, you can impute the outlier with mode or mean or median and mark and create a separate feature marking this object as an outlier. That's also a fair option. In this case, you will keep the information that there was an outlier, but also prevent the model from using this outlier potentially breaking. One of the ways also is to use like another metric, different types of metric, because for instance, If you use some metric regression, maybe the outlier will significantly impact your calculations. But if you have capping or truncated loss, your model won't be affected. Again, a clever way to deal with the outlier. Another way is to use regularization of models, but we'll discuss this during the lecture on machine learning models. And now let us have some code. Hello, and this is the coding session for managing outliers. As usual, we start with mounting the Google Drive with the dataset. We'll use the housing dataset. We'll import the libs. So we're heavily using Scikit-learn's libs, and I highly recommend you to take a look at them. Of course, you can create those methods on your own just by the definitions and the theory behind them, but using Scikit-learn will just save you time. However, if you wanna get into it, if you want to understand how everything works on a low level, I highly recommend try to implement the methods by yourself. Yeah. So let's move on, and we'll use 2 columns for managing outliers here. And we begin with the scatter plot just to take a look at the data. Visually, we can see here some outliers. And let us build the box plot. Once again, yeah, box plot. And you can see the whiskers here. Yeah, those are called the whiskers, like the cat's whiskers. And outliers are marked here. Since that's a ground living area, it is above 0 in any way, so we only have the right hand outliers here. But it is possible to have both sides of outliers, depending again on your data. And since we have the box plot here, let us use the interquartile range IQR method to identify outliers. Basically, we can see them here, but let's just apply some mathematics. To do so, we need to have the 25th and 75th quantiles. Just calculate IQR and like have a lower bound and upper bound that are corresponding to those lines here. Yeah, so just like this, we will have the methods, and we'll also provide the scatter plot with the labels just to take a look at the data. Yeah, so as seen here, we have 75 outliers, all above some value here. We're gonna either build it or just take a look here that is the same as here. Let's take a look at the, well, we're not interested in lower bound. Basically, our data is like above 0. But what about the upper bound? Yeah, so this is this line. Let us calculate the z-score. The z-score is kind of similar. It is based on the normal distribution, and based on it, yeah, we identify here like significantly less outliers than for the IQR. It's 25 actually, so you can easily calculate them. Just use z-score from stats module. Again, you can calculate this on your own. I'm using it just for the simplicity to speed up the whole process. What about the Cook's distance? If you remember the lecture, I was describing the Cook's distance there, and let us use it because we use again predefined Cook's distance. You can calculate it on your own, but I'll use it as is. Yep, and based on the Cook's distance, we can see here that there are a number of items that highly influence the data, the model, the regression model. 172 outliers here. Some of them are located in normal regions for some reason, but yeah, the majority seems to be fair labeled. Let's move to dbScan. So dbScan is a clustering method. It's a density-based method. We will discuss it during the lecture about clustering. What you need to know now is it operates based on density, meaning that it is important how many neighbors are there around and their location and their grouping. For dbScan, you do not need to provide the number of clusters. It can automatically detect clusters, like group the objects into clusters. With this in mind, let us try to cluster the data, and everything that is not in a cluster we will consider as an outlier. Let's take a look. dbScan managed to identify the outliers here, 207. Let us maybe try to take a look at the data set. Let us plot dbScan clusters just to take a look at the whole data, not only on like the outliers detected, but the whole data. As you can see, there are 33 clusters defined. Some of them are like meaningful, some of them are really small. But -1 is our outlier. And you see how dbScan divided kind of layers. But let's move on to the isolation forest. So isolation forest is an algorithm that applies trees to separate the outliers. We can do so since trees are normally built with the entropy as a target, and if you remove the outlier, you reduce the entropy, since outliers are highly impactful. This is the picture of outliers. Again, we can see that the main data remains, just the regions are affected. And local outlier factor is another approach. Personally, I prefer the isolation forest, but maybe we can play around with the parameters here. Well, this is just an illustration. What about one class SVM? One class SVM is another approach to find the outliers. Surprisingly, there is a line detected as an outlier that I believe that should be investigated. And let's visualize all together. So here you can see all the outliers from all the methods at once. I use different colors and different shapes. I don't know whether it is useful or not, but some of the algorithms mark the data similarly, some of them not. One of the ways is just combine several algorithms and use ensembled decision. Yeah, we can also take a look at the data distinguished, look here, and again there's just some notes. And I highly recommend taking a look at the outlier detection document, and I highly recommend taking a look at the Scikit-learn's outlier detection guideline. Please, that's super useful. That's it. Thank you. Welcome back. We're heading to the transformation and encoding. Transformation and encoding are used to ensure the dataset is in a suitable format. Scaling features like age and income ensures that the models aren't biased towards features with larger scale. Similarly, encoding turns categorical values into numerical ones so the model can understand them. Not every model can utilize the categorical data. We'll discuss this during the lectures on machine learning models. And this step is important, and it takes into account not only the data itself, but also the models that will be utilizing the data you are preparing. What about like scaling and normalization? Well, as for scaling, you can have like min-max scaling or normalization, classical normalization. and the data will be between 0 and 1. You can have standardization. Basically, you're trying to have a mean of 0 and standard deviation of 1. And there are also other approaches like robust scaling. They use different logic behind them, and we'll take a look at the robust scaler that is used in Scikit-learn during the practical session or the coding session. As for the transformations, as I mentioned, if we apply log transformation, our data will change. The data will change its shape. The outliers will be not so highlighted. This type of transformation reduces skewness, especially for right skew data, and you can use it for large positive right skewed values, for instance, like transforming sales data to stabilize variance. Yeah, that's also like, or transforming income data. That's also a good use case. And again, always visualize the effects of your data transformation. That really helps, and that might provide you some insights about your data. Another transformation is box-cox transformation. It makes the data more normally distributed, and it's just another type of the transformation that uses power transform under the hood. There is also like a square root transformation. That's simple. You just apply square root to your existing data, and that's it. Another technique is data binning, converting continuous numerical data into discrete bins or intervals. Just imagine the histogram. Creating a histogram requires data binning. There are several approaches to bin the data, like bins can be equal width or like equal frequency or like quantile based. As for the pros, it simplifies the data and reduces the complexity. Sometimes it can even bring interpretability. However, since it simplifies the data, it leads to information loss. Some artificial cutoff points, so you need to clearly understand why and when to use each binning type. This is why I highly recommend that you use domain knowledge to define the bins. For instance, like binning ages into categories of youth, so young adult, and senior. Those are graphs that can help you visualize different binning techniques applied to the existing data set. Why data encoding will now talk about the data encoding. So why it is crucial for machine learning. Data encoding helps us convert categorical data to numerical format, unlike binning. So in binning we converted numerical to categorical. Now we would like to convert categorical to numerical. Those types of encoding allows ML algorithms to use features that are non-numeric, for instance, colors, city names, or genders, and we would like to convert this to numerical. There are various techniques: one-hot encoding, label encoding, ordinal encoding, target encoding, frequency encoding, and binary encoding. What about like one-hot encoding? It's pretty simple. It creates binary columns for each unique category. Imagine we have a feature of color, and well as red, blue, green, and those just separate columns for each color. Yeah, so for instance, you could have like red 0 or 1, blue 0 or 1, and green 0 or 1. Well, actually, if we have only 3 colors in the dataset, we do not need a third one. Yeah, we can have red and blue, and if there are zeros in red and blue, then the green will automatically be considered as 1. But we don't need it, since that brings us the same information as zeros in red and blue. But this is only true if we do not have the missing data or outliers or something like this. Pros of this method: it is simple, it is easy to interpret, but it can lead to high dimensionality. Imagine you're applying one-hot encoding to something like car brand. You will have a huge amount of features. As for the label encoding, it assigns each category a unique numerical value. Like imagine you have pork class, and this can be converted into the numerical. Or you have like animal types: cat, dog, bird, and so on. Well, it becomes 0, 1, and 2. It is simple, it is super memory efficient. Please keep in mind that it implies an ordinal relationship which can mislead models. For instance, If cat is 0, dog is 1, and bird is 2, it doesn't mean that cat is better than dog or cat is, or dog is 1 plus cat, and bird is like 2 dogs or whatever. Keep this in mind. And as I mentioned, yeah, ordinal encoding. This can bring us to the label encoding, but with the categories within the order, like satisfaction, low, medium, high, 0, 1, 2, because low is less than medium and high is more than medium. There is a more sophisticated approach like target encoding. It replaces the categories with the mean or like median or like some functions based on the target. The great use cases like hard cardinality features like zip codes or car brands. Imagine we're encoding the car brand with a medium price. We can do so, and that's super reliable. However, we should be cautious, and because this can lead to overfitting if not handled properly. Please keep in mind that your data might become spoiled because of this technique. We'll discuss this technique during the modeling lectures and practical sessions. I wanted just to highlight that it exists. And we can also encode with frequencies. We can replace categories with the frequency counts, and it's okay for categorical values with many levels, and it has low dimensionality. As imagine we're having a car brand that we would like to encode, and we could encode the car brand as how frequent this car brand appears in the data. And that's it, we just count it. Binary encoding here combines a label encoding and one-hot encoding to reduce dimensionality. It assigns each category a number and then converts this number to binary and splits it across different columns. Imagine like you have a binary encoding of something. The category 5 is a binary 1, 0, 1. And you have those columns, so 3 columns, and 1, 0, 1 is a 5. There are many other techniques, so I won't stop here, but some of them like weight of evidence, hashing, we'll discuss during the next lectures. Just to highlight, well, the hashing is pretty sophisticated approach, but this one helps you reduce the dimensionality. That's pretty interesting and pretty useful technique. And here is the summary of basic encoding technique. You can later review it just to use as a guidance. And this is the summary of advanced encoding techniques. So just take a look at it, use it as a reference. I think you might be bored with this presentation now, and we have another coding session to cover transformation and encoding. Welcome everyone! Today we'll discuss crucial preprocessing techniques for data used in machine learning. Our focus will be on category encoding, scaling, transformation, and binning techniques. Each technique plays a crucial role in preparing data for models, ensuring higher accuracy and robustness. Let's dive in. We start as usual with mounting the Google Drive and loading the dataset. And we start with category encoding techniques. I'll start with the toy dataset just to show you different techniques on a small portion of data, just for you to understand how the things are calculated. And category encoding is used to convert categorical variables into numeric formats that machine learning models can understand. I'm using the category encoder slip, and I highly recommend it. It's super useful. Please pay attention and play around with it. So this is our data set, nothing special. Let's move on. We start with one-hot encoding. One-hot encoding creates binary columns for each category. And since we're using a toy data set, categories like A, B, and C are represented as binary columns. Let's take a look at it. Yep, that's it. We can even plot it and show it as a heat map. And here you go. We're moving to the label encoding. Label encoding assigns a numeric value to each category. For example, categories A, B, and C become 0, 1, and 2 respectively. This technique is more memory efficient, but may introduce an implicit ordinal relationship that isn't always correct. And here, like the ordinal encoding, it is similar to the previous one, but in ordinal encoding, we can define the sequence, the order of the categories. And sometimes it is useful, but yeah, please pay attention to it. Binary encoding. So binary encoding, it's a balance between one-hot and label encoding. It uses fewer columns than one-hot, but preserves more information. It is suitable for high cardinality features, like features with many categories. We're moving to the more sophisticated ones. It's a frequency encoding. What frequency encoding does replace each category with the frequency in the dataset, and categories that appear more frequently are given higher numerical values, which can be useful for certain models that benefit from frequency information. Just to double check, yes, those are the frequencies or the counts. And let's move to the target encoding. It involves replacing categories with the mean of the target variable for that category. Here we're using the target encoder from category encoder sleep, but we can create our own custom cross-validated target encoder, and you can also create your own. The numbers here differ a little bit. However, it is due to the fact that in the category encoders, the encoding is more sophisticated than the one we used here. And I highly recommend taking a look at the category encoders. We're moving to the transformation. Data transformation can help stabilize variance, normalize distributions, or make the data more interpretable by models. And we start with log transformation. It is used to handle skewed distribution. Here we're using the lot frontage column. This technique helps compress larger values, making the distribution more normal, more bell-shaped and centered, I would say. We have another distributions box-Cox transformation. This is a power transform. It works on positive values only. This distribution can also help with skewness, and it does so. Transforms the data in a different way than the log distribution. Here we also have the square root transformation. It helps with moderate skewness, and this transformation is especially helpful for count data where values range from low to high. And going back to encoding, I'll just show the encoding on the real data set, not on the toy example. Here you can see on the original data a lot of new columns were created just to transform this one into like one hot representation. Let's take a look at the label encoder, and we're moving to the binning techniques. And binning is a technique for discretizing continuous variables. If you remember the histogram, that's what it does. So we're converting the value into some set of buckets. Here we're using the same data set. I'll just refresh it. The numeric column for this will be the sale price. And just let us plot it compared to the index. By the way, you could notice here a very interesting shape. I think it's worth investigating, like this pattern. Let's leave it for the next sessions and focus here on binning techniques. And we start with the equal width binning. The range of values is divided into equal sized bins. In our example, sale price was binned into the equal bins, so 5 bins. It is similar to the distribution maybe. Let's move to the equal frequency binning. Equal frequency binning has approximately the same number of data points. It helps ensure that each bin has the same representation, which can be useful when the data is highly skewed. Because here the data is definitely skewed for the sale price, but yeah, let's take a look here. Here we binned the data. And we can also have the custom binning. It's based on domain knowledge. We can define custom binning, and here we created the binning sale price into medium, low, very high, and high. and the frequency of the spinning. Yep, so again, histogram is also a binning technique. Let us plot the histogram. Let's take a look at it. Yep, it is also binning technique. Let us have the 5 bins. And 5 bins here are similar to the binning technique that was used here, equal width binning. So that's it. And as a conclusion, so choose the right technique. Choose scaling, encoding, or transformation based on data distribution, the model you are using, and the feature type. Try to avoid data leakage. Always use cross-validation when encoding based on the target variable to prevent overfitting. And visualization matters. Always visualize your transformations to ensure you understand the impact on your data. And that's it. Thank you. Hello, and let us continue. Common data pre-processing challenges. In real-world data preparation, there are challenges. Some of them come with ethical considerations. It's bias handling, fairness, and transparency. Like, imagine missing data. Missing data can lead to biased models, and biased models might not be ethical, so they will treat some groups unequally, or they will just have poor performance. This is the thing you need to consider. And the same goes with outliers, so they can damage the model performance. We didn't cover like the mixed data types during this lecture, but again, keep in mind that handling numerical and categorical data requires thoughtful pre-processing and encoding. You should know which feature is of which data type and why, because sometimes you can mix them up. And of course, the scalability, processing large data sets that cannot fit in memory and that requires efficient pre-processing strategies, including memory management, distributed processing, batch processing, or sampling, and even sophisticated methods to calculate statistics, because if your data set is not fitting into the memory, it might be tricky to calculate standard deviation, mean, and other characteristics. Let us wrap up. Today, we covered key techniques in data preparation: cleaning, transformation, encoding, and handling outliers. And each step contributes to the overall success of a machine learning project. And high quality data means high quality models, and the time spent preparing your data is always worth it. If you can invest either in data or in model, I would recommend investing in data. And I recommend you to experiment with various techniques. And remember that every dataset is unique and it requires its own approach. And of course, domain knowledge and understanding of the domain. And some final thoughts. So, data preparation is the backbone of the machine learning. Even advanced algorithms cannot fix spoiled data, making quality preparation crucial. Take your time with the data, understand it, identify missing values, distributions, and outliers. It is worth the effort. Experiment and iterate, test different cleaning, transformation, and encoding techniques. Please document everything. Keeping a clear record ensures reproducibility and supports collaboration. As I mentioned during the start of the lecture, in the end, you should have the document or the dataset card describing how you ended up having this dataset, which steps were applied, which methods did you use, and what was your idea behind applying each of the methods. Real-world datasets are messy, so effective pre-processing helps turn messy data into meaningful insights. Be thorough, experiment, and always remember, good data preparation unlocks the true potential of machine learning. Thank you for attention and have a nice day.